Welcome to our unit on aqueous reactions and solutions. This first presentation is mainly a review of solutions terminology to bring back some information that you learned in your Regents class. So first thing is vocabulary. A solution is a homogeneous mixture of two or more pure substances. So homogeneous, remember that the solute particles are dispersed uniformly. That's the key throughout the solvent. You will not be able to see the solute particles when the solution forms. You cannot, and because of that, because they're so microscopic, you cannot filter a solute out of the solvent. There's a lot of different types of solutions you can see here. What you're most familiar with probably would be a solid dissolved into a liquid, like that, but there's plenty of solutions. So like the air that you breathe is a solution. It's a homogeneous mixture. Brass, soda, all different types exist. In this class, you're mostly going to be dealing with solids and liquids or liquids and liquids. When you see the term aqueous solution, that just means that the solvent that you're dealing with is going to be water, and that will be denoted by an AQ in parentheses in the formula. Some solutions are electrolytes. They will conduct an electric current. The stronger the electrolyte means that there's more charged particles in the solution. If it's a weak electrolyte, there's fewer ions, and a non-electrolyte will dissolve but will not conduct a current. There are different reasons why something could be a strong or a weak electrolyte. It could have to do with the bonding strength. It could have to do with the quantity of the particles due to molarity. So there's just some different examples here. So if you have many charged particles, you're going to have a stronger electrolyte than if you had fewer charged particles than if you had none at all. So if you want to just pause for a second here, think about this list and what would be an electrolyte or a non-electrolyte. So pure water would be a non-electrolyte, whereas tap water would be a weak electrolyte because there are ions present in your water that are put there intentionally by the water authority, also due to contaminants, hopefully very, very small concentrations, or just corrosion from pipes. A sugar solution would be a non-electrolyte because sugar is covalently bonded. When it dissolves, it does not ionize like something such as sodium chloride will. So sodium chloride is ionic. It fully dissociates into the water and will conduct a current. Hydrochloric acid is a strong electrolyte. Strong acids are strong electrolytes. Lactic acid, it is an acid, but because it's an organic acid, it would be weak. You do not need to memorize a list of weak acids because there's so many of them. Ethanol, covalently bonded, it does dissolve in water, but it does not conduct electricity because the ethanol is covalently bonded. Pure sodium chloride, meaning the solid, just table salt, will not conduct electricity. Ionic compounds will only conduct electricity under if they're dissolved or if they are melted. So they will not conduct electricity in the solid form because the ions are not free to move. The reason why so many things are present in aqueous solutions is due to the nature of the water molecule. So water is known as a universal solvent, a common solvent, because it is polar. Now this is something that you learned in Regents chemistry, if you recall, the mnemonic device SNAP. Symmetrical molecules are nonpolar. Asymmetrical molecules are polar. Water molecules are asymmetrical. They have an unequal distribution of charge due to the unequal electronegativity values of the hydrogen and oxygen, which gives the water molecule partial positive ends at the hydrogen and a partial negative end at the oxygen. Very important that you understand that. And there are two lone pairs of electrons. When we get into molecular structure, you'll be able to draw this in your sleep. So this image just shows you how water molecules would be able to dissolve an ionic crystal. You see the positive and negative charges here. The water molecules would orient themselves such that the positively charged hydrogen ends are adjacent to the negative ions and the negatively charged oxygen ends are adjacent to the positive ions. So here, these should be arrows. These equations just show you how you would write the dissociation. I'm not sure why these subscripts didn't translate well in this program, but anytime you see those, and these should be superscript charges, you can see how an ionic compound would dissociate. So dissociate means to separate. So sodium chloride, when you dissolve it into water, the positive sodium ions would separate from the negative chloride ions. If you have a compound containing a polyatomic ion, such as the nitrate would stay intact. Again, this should be written in this way. Now, for something like magnesium chloride, when you do have two chloride ions present here, when you write the two chloride ions, you want to put that subscript of a 2 as a coefficient in front of the ion to show that there are two chloride ions, each possessing a -1 charge. You don't want to do something like this because that's implying that you have a unit of Cl2 that's carrying a -1 charge. But by writing it as 2 chlorines -1, that means that I have two ions that each carry a -1 charge, and that would offset the singular positive 2 charge that the magnesium possesses. And the same thing would apply for the sodium sulfate and the aluminum chloride. Let me see here. Okay, so when ions dissolve into an aqueous solution is due to the polarity of the water molecules. That just reviews that structure. And something that you'll learn as we get into acid-base chemistry some more later in the year is that weak acids can partially ionize in solution, and strong acids do as well. Because acids, if you look at the formula, for example, for hydrochloric acid, HCl, hydrogen and chlorine are both nonmetals, which would mean a covalent bond would form between them. But the attraction that the negative portion of the water molecule has for the partial positive polar end of the HCl molecule is so strong that the hydrogen actually transfers over as an ion, forming this H3O hydronium ion and leaving the chloride ion in solution. And if you remember from acids and bases in Regents chemistry, the presence of hydronium ions is indicative of an acid solution. So, hydrogen ions or hydronium ions are going to drop your pH value. So you would have no HCl's in a solution of hydrochloric acid and water. They would all ionize in this way. Strong acids will completely ionize in solution. There are other strong acids. When we get to acids and bases, you will have to memorize 6 or 7 of them. And those are the 6 or 7 strong acids. They're always going to completely ionize. Any sort of calculations will be real simple with those. There are plenty of weak acids as well. Organic acids tend to ionize less. And that's a whole other branch of calculations that we'll work on later in the year. It's just that some of the hydrogens will get pulled off of them, but not all of them. You will not have to memorize a list of weak acids because there's way too many. As long as you memorize the strong acids, then anything else is going to be weak. There are energy changes involved in the dissolving process as well. There are actually 3 steps in forming a solution at the chemical level. You need to separate the solute particles from one another. You need to expand the solvent particles from one another so that the solute has room. And then you need to put the 2 together again. And all 3 of those processes involve changes in energy in some way. And we refer to that as delta H, or change in heat, or heat of reaction process. They can be positive or they can be negative. And if you remember, a positive delta H value is an endothermic process, and a negative delta H value is an exothermic process. So when these processes happen, you see step 1, step 2, step 3. When you add all of the delta H's of all 3 processes together, you get the overall change in heat for the entire process of forming that solution. And that overall could be positive or negative. Normally, the first 2 steps of taking the solute particles apart and taking the solvent particles away from each other. Usually those are endothermic processes, because you are breaking things apart. And then normally the process of putting them together will be a negative delta H value, or exothermic. Now, depending on the actual quantities of those positive and negative numbers, when you add those together, that will tell you whether the entire process would be endothermic or exothermic. So that's why when you dissolve some things in water, like sodium hydroxide, for example, it releases a lot of heat, because the process of the sodium and hydroxide ions combining with the water, that process has a larger negative delta H value than the processes of breaking apart the sodium and hydroxide and separating the water. Whereas other dissolving processes would be endothermic. So the container, if you felt the walls of the container, it would get colder. This just goes through that again. The changes overall for the solution are a result of the sum of these three processes. This is called Hess's law. When we go into thermochemistry and thermodynamics in a few weeks, you'll see this in a lot more detail. And these are just graphs that would show that process as well, that if you have these positive delta H values and a negative delta H value overall, you could have a drop in energy, or you could have a not so large or drop in energy, or an actual increase overall. This is just an image talking about, these are the ones that you really need to take a look at. If you have a polar solute and a polar solvent, or a nonpolar solute and a nonpolar solvent, you're really going to result in the formation of a solution, something that you learned in Regents chemistry, and just remembering the like dissolves like. Again, you'll see this a lot more when we get into molecular structures at the end of the course. And there's just some examples of nonpolar and nonpolar, and then polar or ionic substances dissolving into polar solvents. And that has to do with the molecular structures. Factors affecting solubility is something that was covered in Regents chemistry. So the structure of the molecule obviously has to do with the solubility of a substance. Pressure will have an effect only on gaseous solutes. And then temperature will affect the solubility of solid liquids and gases in solution. You do not need to know this calculation, but Henry's law is a mathematical relationship between the pressure of a gas and the solubility of that gas in solution. What you need to remember is that the greater the pressure, the greater the solubility of the gas. Basically, when you apply pressure to the container, you're confining the gas and keeping those molecules closer together, where they will be forced to interact with the solvent particles more than if you had pressure above it. So that's why when you open a brand new bottle or can of soda, why you get that gas escaping, because you're releasing the pressure and therefore decreasing the solubility of the gas. For most solids, in terms of temperature, most solids will become more soluble in water as you heat them. So if you think about, dissolving sugar into iced coffee versus the same quantity of sugar into the same quantity of hot coffee, you can dissolve a lot more sugar in the hot coffee. Because you have faster moving particles, you're more likely to separate the particles from one another when they're heated up. Whereas gases will always decrease in solubility the warmer they get, because when you heat up a gas, the particles again move faster. What do gases do when they heat up? They expand, so you're less able to confine them at higher temperatures. Now in Regents chemistry, you had a reference table G that was the solubility table that had a whole bunch of different solutes dissolved in water and showing how their solubilities change with changing temperatures. So this is just kind of a snippet of that. You would need to be able to interpret this. You did this a lot in Regents Chem. You could find a lot of different tutorial videos on how to use reference table G. We'll look at a couple sample AP problems, but overall it's a pretty self-explanatory graph. These are gases, and you can see that all of these gases decrease in solubility at varying rates, but they still do decrease in solubility as the temperature increases. Remember the terminology for saturated versus unsaturated solutions, that if you have a solution that's holding its maximum amount of solute in a certain quantity of solvent at a particular temperature, that solution is saturated. Any other solute that you would add to that solution would settle to the bottom. It would not affect the concentration of that solution. It would be a constant. the rate of new solute dissolving would have to equal the rate of solute crystallizing out of the solution. So the rate of dissolving would equal the rate of undissolving, if you will, but the concentration would remain constant. If you have a solution where you did not max out the quantity of solute that could dissolve into that quantity of solvent, it would be unsaturated. So if you did continue to add solute to that solution, you could increase the concentration, the new solute would dissolve. Certain situations could result in supersaturated solutions. If you heat up an unsaturated solution and then continue to add more solute and then cool it down, you kind of can trap the excess solute particles in it, resulting in a supersaturated solution. So if you make like rock candy or something like that, that would be an example of a supersaturated solution. So in terms of characteristics of solutions or factors affecting solubility, you would be able to dissolve more solid into a solution if you heat the solid, if you agitate it because you're putting more solute particles in contact with solvent. Also, if you grind it into small particles, because that would increase the surface area, like a lump of sugar versus granulated sugar. Gases will be more soluble when they're cold and under pressure. So think of new soda. When you think of how soluble the gases are, the CO2 will stay dissolved if it's cold and if it's under a lot of pressure. If you want to separate the components of a solution, again, you cannot filter the particles out. You cannot pass them through a filter and separate the salt from the water, or a lot of potable water issues would be solvable. You have to distill them. Distillation is due to different boiling points. Different boiling points are due to differing strengths and intermolecular forces. The stronger the intermolecular forces, the more difficult it is to separate the particles from one another. Another way to separate the components of a solution of liquid in liquid would be chromatography. You learned a little bit about this, and you might have done something in Living Environment or AP Bio with chromatography, and we discuss it briefly in chemistry. We'll probably do a chromatography lab at the end of the course. Chromatography works because different solutes have different affinities to the solvent versus the paper due to intermolecular forces again. So particles that are more attracted to the solvent are able to be drawn up the chromatography paper farther than particles that are less attracted to the solvent / more attracted to the paper, and there's a calculation involved in that. So that pretty much wraps up basic terminology and characteristics of solutions. In the next presentation, we'll get into some review calculations such as molarity of how you can calculate solution concentration.